And welcome to the 608th meeting of the Lexington section of the ACS. Welcome tonight. I'd like to point out to any of you that might be interested that the 1991-92 National Chemistry Week is going to be with a little bit more gusto than we've had for the last couple of years, probably like the first year we had when Audrey was running the section. And if any of you are interested, graduate students, faculty, are interested in being involved in that, please don't hesitate to give me a call. Also, any of you who might be interested in being involved in the Chemistry Olympiad, I'd love to have your help and support in getting in touch with high schools in the Lexington section area. So I guess that's a warning that I may be calling a few of you. I'd like to introduce our speaker for tonight, Brian Hansen from Virginia Tech. Let me tell you a little bit about Brian. There's a few of us here that know something about Brian from our past, but we'll keep it business-like since he is a gentleman. Brian has his BA and MA from Johns Hopkins University and his PhD from Texas A&M under the aegis of Albert Cotton. We can hear cheers or hisses, whatever, but a well-known chemist, inorganic chemist. Brian then spent a year and a half at University Chemical Laboratory in Cambridge, England as an NSF National Needs Postdoctoral Fellow. And then in 1980, Brian joined the faculty at Virginia Tech, where he is now full professor of chemistry, or professor of chemistry. A couple of years back, Brian was honored as a recipient of an Alexander von Humboldt Fellowship in 1987 in Germany, and an honorary Ramsey Memorial Fellowship in 1978. His interests include solution and solid-state dynamics of metal carbonyls and reactivity of metal carbonyl dimers, molecular structure of adsorbed metal carbonyls and metal oxides, immobilization for supporting organometallic complexes, and homogeneous and heterogeneous catalysis. Tonight his talk is going to try to bring it all together in what he calls a brief history of metal carbonyls. Brian?
Well, thanks, Alan. It's certainly a pleasure to be here. I think I visited the University of Kentucky some years ago, 8 years ago, shortly after I got started on the faculty of Virginia Tech. When I got Alan's phone call, I was really pleased to be able to come back and share some chemistry with you again. And I thought that this might be a nice occasion to put my small contribution to metal carbonyl chemistry into the context of the history of metal carbonyl chemistry. So a lot of the material I will talk about tonight will be of general interest, I hope, and traces some of the chemistry of metal carbonyls through the years. Speaking in 1990, it's a good time to do this perhaps. The very first binary metal carbonyl was made a little over 100 years ago and was reported in the chemical literature in 1890. So we were celebrating the centenary of metal carbonyl chemistry. If we could start then with the first slide, I guess I can bring that forward. Jack asked me where I was going to start with metal carbonyl chemistry, and I told him with nickel carbonyl. And he says, well, why not with the first one? And why did you choose nickel carbonyl? And the answer for me is that this is the first binary metal carbonyl, and most of my interests have been with the binary carbonyls, at least in terms of the structure of these compounds and in looking at some special aspects of the solid-state dynamics of these. The first metal carbonyl then was platinum dicarbonyl dichloride, which precedes Mond's work by about 20 years. So Mond was aware that carbon monoxide could perhaps combine with metals, but he was quite surprised, I think, to find nickel combining with carbon monoxide under relatively mild conditions, and he got the composition of this compound correct in the first shot, decomposing it to carbon monoxide gas and doing gravimetric analysis on nickel metal, and the carbon monoxide evolved. He came up with the correct formula. Also, he describes in this paper a technologically useful application for generating nickel carbonyl. So not only did he discover a brand new class of compounds, but a technologically important procedure for the purification of nickel metal from cobalt metal, which we've referred to now as the Mond process. Having got his feet wet in the area, he quickly went to work to find other compounds, and of the other metals that combine directly with carbon monoxide, iron is the only one that does it at accessible temperatures and pressures. And here, a year later, he shows that finely divided iron will combine directly with carbon monoxide. It turns out at high temperature and pressure. Here he missed the composition. He formulates it as iron tetracarbonyl by analogy with iron pentacarbonyl. It's not clear why he got it wrong. His gravimetric analysis was probably pretty good, but perhaps he was generating some iron carbide and not getting the correct composition. So the very first two then were made by Mond some years ago, and a bit of a mystery at how these compounds should be put together, volatilizing iron and nickel, and then releasing the pure metal in the metallic state when the compounds are decomposed. Now, people became very aware very quickly that of these two compounds, the iron compound, iron pentacarbonyl, is photosensitive. The nickel carbonyl, turns out, is not very photosensitive, but the iron pentacarbonyl is a liquid, decomposes in light. And in really a very, I think, nice paper by Dewar and Jones at the beginning part of this century, they look at the photolysis of iron pentacarbonyl and synthesize the diiron nonacarbonyl, which becomes an important player in the history of the metal carbonyls, at least in terms of defining structure and function of the bonding in these compounds. And he also got the photochemistry basically right too. He postulates that the iron pentacarbonyl will absorb light and kick out a carbon monoxide ligand, we would now say, to go to the iron tetracarbonyl, and that this would combine with the iron pentacarbonyl to go on to the dimer. And I like the very last sentence in this manuscript, in fact, is highlighted in blue here. The work was done in England, and his photoreactor was a flask in the windowsill, and he reports that he will tell us something new about the metal carbonyl chemistry when the necessary sunlight becomes available. I thought it was, upon reading that, it's a good thing that he wasn't competing with people in Arizona at the time, because he certainly would have been scooped. Now, as far as the photochemistry, people still look at photochemistry, of course, of metal carbonyls, and it turns out that photolyzed iron pentacarbonyl generates very active catalysts for the isomerization of olefins. And as recently as 81, Wright can say that, or says that this is a reasonable reaction at the top here. I just have a pointer for the initial photoreaction of iron pentacarbonyl, the ejection of carbon monoxide. And he also proposes that this can go on ultimately to the iron tricarbonyl, which is the active, he postulates as the active catalyst. Well, this is what Dewar and Jones had postulated some 70 years previously. And we now accept that to be the correct entry into the photochemistry of the mononuclear carbonyls. Mond, of course, is staying active in this, and I'm sure that this is an impossible slide to read, but on the left here, at the beginning part of this century, are the metal carbonyls that Mond was successful in synthesizing. These are the nickel, the cobalt, iron carbonyls of composition, the pentacarbonyl, the diiron nonacarbonyl, and Fe, what he calls FeCO4, which is a solid now. And we will come back to this compound again and again, of course, in the course of the evening, with regard to some structural aspects of metal carbonyls. Molybdenum and ruthenium carbonyl he had, but he has a question mark on his composition, its density, melting point, boiling point. What he does have the compound, in fact, is the correct orange compound it looks like, which we now recognize to be tri-iron dodecacarbonyl. In the cobalt carbonyls, he made one of composition cobalt tetracarbonyl, which we now, and he has the structure correct as well as a dimer, dicobalt octacarbonyl. This compound, then, that's been known for some 80 years, is arguably the most important of the metal carbonyls, at least from a technological point of view. This one's made on the tens of thousands of pound scale in this country as a use and used in oxocatalysis for the production of aldehydes. Now, as far as the composition of these compounds, they're quite remarkable, and people really lack theories for how they're put together. In the early part of this century, Lewis, of course, came up with an octet rule for carbon chemistry, and people were happy to count to 8 electrons to understand the valencies of carbon. Langmuir, it turns out, I think, is the first one to count to 18, which all good organometallic chemists do in the back of their head. And he noted that if you take the compositions iron pentacarbonyl and nickel tetracarbonyl, the valence shell then contains 18 electrons, which would be the appropriate shell for the filled valence shell out to the next noble gas. We now refer to this as the effective atomic number rule. Langmuir initiated it, but as we'll see in a few minutes, Sidgwick popularized it and showed that it was far more useful than just the simple binary metal carbonyls. Now, the Germans rightfully get a lot of credit in the early part of metal carbonyl chemistry. This is sort of a sidelight to the theme of tonight's talk, and this has to do with the discovery of the oxo process, which really stems from Fischer-Tropsch chemistry, which was done in the late 20s in Germany. Fischer and Tropsch postulated or discovered the Fischer-Tropsch, what we refer to as Fischer-Tropsch catalysis, the combination of CO and hydrogen to hydrocarbons. And it turns out some people at Pittsburgh, what we now refer to as PETSI, the Pittsburgh Energy Technology Center, but the corresponding Bureau of Mines lab in the 30s, added ethylene into this reaction mixture and report that they generate oxygen-containing compounds. And it just sort of languishes there in the literature, I think, for a while. And Rolln repeated this work. He thought it would look pretty interesting, and he figured out that he was making aldehydes and alcohols over what was a heterogeneous catalyst. During the war, apparently, Rolln and independently, people in the United States determined, in fact, that the active species is a hydrido-cobalt tetracarbonyl, which has some interesting structural aspects of its own, and we'll come back to some solid-state NMR work on a similar molecule, at least in terms of its structural chemistry. So there's been a long association, in fact, between metal carbonyl chemistry and industrial chemistry and applications to catalysis. And a lot of the pioneering work, of course, was done in industrial labs. Also in the 30s, Heber, which is sort of the father of modern metal carbonyl chemistry, synthesized just an incredible variety of compounds. I show one of the more useful ones, at least in terms of entry into some interesting compounds. It's something that he refers to as the Boson reaction, or the base reaction. And he noticed that many carbonyls, and in this case iron pentacarbonyl, undergo a disproportionation reaction with base to give first the simple anions, and upon protonation this dihydride, which is the best entry now into the synthesis of the original compound of composition FeCO4 that I mentioned, which we now recognize to be tri-iron dodecacarbonyl. So the oxidation of this compound goes to a trinuclear cluster of irons. Now Heber did some other interesting things as well. In addition to developing a good synthesis for tri-iron dodecacarbonyl via the Boson reaction, he determined the correct molecular formula for this green FeCO4. And the way he did the experiment is rather intriguing, especially to those of us that know something about the properties of iron pentacarbonyl. He did cryoscopy. Actually, I saw a freshman over at Transylvania doing a freezing point depression just this afternoon. That's the experiment he did with this FeCO4, but the solvent for the compound now is neat iron pentacarbonyl. It's a highly toxic, oily liquid, and he determined the structure to be the trimer Fe3CO12. And he proposed many structures. His nomenclature was Fe with the superscript 6 to mean that the iron is 6-coordinate, and he postulated bridging carbonyls in one of his structures between two irons in this linear type fashion right here. Now, shortly after that, Sidgwick came back and looked at this electron counting schemes for inorganic compounds and followed up on the aspects of the chemistry that I had mentioned that Langmuir did in counting up to 18 electrons. Now Sidgwick defines the effective atomic number as the actual total electron count rather than the valence electron count, but we can see that it would give us the same result. 36 would be the corresponding electron count for the noble gas past chromium and iron and nickel, 54 for the one below molybdenum, and so on. And he says that the metal carbonyls that have odd atomic numbers for the metal don't form simple mononuclear carbonyls. And at the time that was a true statement, and even since then there's only been found one exception to that rule, and he found that to be remarkable, but it's quite easy to understand it with our understanding of the bonding in these compounds now. But he goes on, and I think his real contribution is to look at compounds that contain more than one metal in the metal carbonyls, and he comes up to what is a rather intimidating formula for relating the atomic number of the metal M with the atomic number of the next noble gas, and he finds that when he divides through by the number of metals in the cluster, he gets these effective atomic numbers of 35, 34 for the dimer and trimer of iron. We now see that that one's one short of the correct effective atomic number, and in FeCO3 it's too short of the effective atomic number. And by looking at that, he realized that these compounds want to achieve that effective atomic number and will look for electrons someplace else in the molecule. He didn't accept the possibility that there might be metal-metal bonds that we now accept, and he perhaps should have accepted from an understanding of organic chemistry and how carbon can achieve its octet in some extended compounds where carbon-carbon bonding is important. So he proposes the structures on this slide, where we have the diiron nonocarbonyl with an iron to carbon to oxygen to iron bridge. This one, in fact, if you consider oxygen to be a 2-electron donor to iron and carbon to be a 2-electron donor to the other iron, in fact satisfies the effective atomic number rule. It also has a structural feature with this bridging carbonyl in a linear fashion that wasn't actually observed in a compound until the mid-70s for this type of compound. For the tri-iron compound, he has this complicated series of carbon, oxygen, iron bridges again in a triangle. This one, everything can manage to satisfy the effective atomic number rule. He has trouble, though, with the tetracobalt dodecacarbonyl in terms of getting everything to add up to the effective atomic number rule with these linear bridges. So he's on the right track. He's got the irons, in fact, in a triangle, and it's the first to consider these cyclic structures for Fe3CO12. Shortly after that, it was shown in actually the first crystal structure of a metal carbonyl by Powell and Evans in the latter part of the 30s, done by hand it turns out. All the intensity data is collected by hand and film techniques. They get the correct structure for Fe2CO9, and now we have bridging carbonyls between three bridging carbonyls between two irons. And to look back at Sidgwick's effective atomic number rule, you in fact have to postulate an iron-iron bond between the two iron atoms to get everything to add up. And we now accept metal-metal bonding as the standard in these compounds, and we find that all the time. Now that structure was reported in 1939, and it turns out to be really quite a feat that this one was perhaps the first, not just the first metal carbonyl to have its structure determined, but the first of a large number of molecular inorganic compounds. The compound just does not want to crystallize. Cotton and Troop, as recently as 1974, went back to redetermine this structure to see if, in fact, it was well known that the structure was probably correct, but to update it and solve the structure by modern crystallographic techniques. Jan Troop is an interesting fellow, and he has a lot of patience. And upon buying a bottle of this compound from Pressure Chemical, and he went through it almost crystal at a time. He's probably scanned hundreds of crystals, and one of them stood out. If anyone who's ever made this compound, you know how remarkable these dimensions are for that crystal. It's almost a block. The compound looks like mica. It's flaky, it's flocculent, and very poorly crystalline. And Cotton says that continued searching has not located another such crystal. I don't know how long anyone has bothered to look since then, but they've redetermined the structure in the 70s. As far as ways of looking at metal carbonyls, the technique of infrared spectroscopy came on the scene in the 40s, and people started looking at these compounds by infrared spectroscopy. And Shaleen and Pitzer did the infrared spectrum that I've shown here now for diiron nonacarbonyl. And an important feature comes out of this, that he sees basically three bands in the infrared spectrum, and one of these, based on the structure, the one at the lowest energy, or lowest wave number, he assigns to the bridging carbonyl. Then if we go back, we see that diiron nonacarbonyl has. So at this time, chemists have X-ray crystallography, which is very, very difficult to do at that time on metal carbonyls, and infrared spectroscopy, and at least in terms of trying to generate structures for these compounds. And they relied very heavily on infrared spectroscopy to try to determine these structures when they could. One that was made at about this time is dimanganese decacarbonyl, which the mass spectrum here is reported in 1949 and shows a series of dinuclear ions, monopositive ions, that leads to the conclusion that this is a compound that has a dimeric structure. And that follows, in fact, from the necessary electron counting argument for dimanganese decacarbonyl. The correct formula is Mn2CO10 for the molecular or parent peak, and they don't find it here. The infrared spectrum, also reported now in 54, and up here, Lynch and others on the roof have reported that in 1954 for dimanganese decacarbonyl and some closely related molecules. And now they don't find the characteristic bridging carbonyl, and they postulate that this compound that has a dimeric structure should not have any bridging carbonyls. And in one of my most favorite papers of the metal carbonyl chemistry, in fact, was published by Cotton and Wilkinson, famous authors of inorganic chemistry textbooks. And this just shows, I think, one of the pitfalls of using simply infrared spectroscopy to do structural determination. By group theory, you can determine from the number of infrared bands predict the number of allowed infrared bands, and then try to match a structure with the infrared spectrum. And the problem here is that there are 3 carbonyl stretching frequencies that we saw in the previous spectrum, and there are only 2 carbon to metal stretching frequencies. And so that led them to rule out, in fact, the correct model for the structure. And they proposed these 2 fascinating structures, one with a tetramer of carbon monoxide bridging between 2 metals, and one with a hexamer of carbon monoxide bridging between 2 metals. And in the very next year, of course, a name that we'll see again and again, Larry Dahl, comes and reports the correct structure is determined by X-ray crystallography for dimanganese decacarbonyl. And it's a little hard to see. This is taken out of his manuscript. There is a dimeric structure, and there are no bridging carbonyls as expected now from the infrared spectrum. We don't find carbonyl stretches now in the infrared. We don't postulate them anymore. And diuranium decacarbonyl has a similar structure as well. At the same time, Dahl and Rundle report their first investigation of the structure of Fe3CO12, which is this interesting compound that Hebert had done the cryoscopy on and shown to be a trimeric structure. And now Dahl and Rundle show that the compound is disordered in the solid state and gives 2 superimposed images of iron triangles to give this Star of David type pattern that becomes fairly familiar to those who have looked at this compound over the years. But has no other structural information about how the carbonyl ligands are arranged around those 3 iron atoms. Now, Sidgwick had made the postulate that no carbonyls with an odd-numbered metal has a mononuclear composition. This would violate the effective atomic number rule. And the Italians, not Ercole, Calderazzo, and others, reported first in an Italian journal and then later in Jack's the synthesis of vanadium hexacarbonyl. And they did this and had it correct. And by the time this Jack's article came out, in fact, the crystal structure was reported very close to that, and to show this argument to be correct. In fact, it doesn't satisfy the 18 electron rule or effective atomic number rule, and it's a paramagnetic compound with an unpaired electron. It's interesting that Pruitt and Wyman, who were at Union Carbide at the time, synthesized what was surely the same compound. They call it a dark blue volatile solid. And they published this in Chemistry and Industry. And when you look at the submission date and the publication date, they were about 3 weeks apart. So I think they must have heard about this first Italian paper, tried to get something in print quickly, and postulate that in fact it's divanadium dodecacarbonyl, which would in fact follow from the 18 effective atomic number rule and argue for a vanadium-vanadium bond. But that doesn't happen. In fact, this paramagnetic compound satisfies the 18 electron rule, but not by dimerizing, but by readily accepting an electron to go to the corresponding metal carbonyl anion. So at this point, we can sort of summarize where we find the binary metal carbonyls on the periodic table. And I've tried to show with 2 different types of typeface here where the simple binary carbonyls have been found, from vanadium to nickel in the first row, down to tungsten to iridium in the 3rd row. Technetium, the metal carbonyls have been made. Of course, they're radioactive, and not too much chemistry has been done there. The niobium and tantalum carbonyls are known principally as the corresponding anions and not the neutral metal carbonyls, although there's some matrix isolation chemistry that has been done with these 2 metals and postulated to show neutral metal carbonyls. And with palladium and platinum, there's no corresponding neutral carbonyl of the same composition of nickel tetracarbonyl, but an incredible variety of metal cluster anions have been found for palladium and platinum, which have no other ligand other than carbon monoxide, and sometimes a hydride. So if we come back to my own interest in these types of compounds, it initiates with Fe3CO12, and so I want to give some additional background on that before I show you some of our work on the dynamics of this compound in the solid state. And it was interesting that the first person or people who first gave the correct structure of Fe3CO12 in the literature was a Mossbauer spectroscopist. And these people, by looking at the Mossbauer spectrum of solid Fe3CO12, showed that there are two different types of iron atoms. And when you combine that knowledge with a triangular structure for Fe3CO12, you come to the conclusion, as there's a typo here, that structure E is the way it's stated in the text, is the correct one. And that's this one here, has the triangular structure with two bridging carbonyls. And in the same issue of inorganic chemistry in '65, Dahl comes in and he's done the crystal structure of the hydride, HFe3CO11-, where now H-, he argues, could occupy a position that CO has vacated in going from Fe3CO12 to the hydride, and he also gets the correct structure for Fe3CO12. That he shows two orientations of it here. Dahl went on in the late 60s to get the structure more completely correct in about '68 with a student named Wei. And then finally Cotton comes in and redetermined the structure, and this shows an Ortet type diagram with the triangle of iron atoms in here, two bridging carbonyls, one above and below the plane. These are the two unique irons, and these are the two equivalent irons, and the unique iron is in the back. And I want to point out these thermal ellipsoids, which are very elongated out of the plane here of the three iron atoms. That leads to some interesting speculation about the motions that are allowed in the solid state for this molecule. This shows a packing diagram putting back into the information the disorder in Fe3CO12, showing the two orientations of the two iron triangles, and the packing diagram in the crystal lattice, or at least part of it. Now I want to leave that structure is correct, and I want to introduce now the aspect of metal carbonyl chemistry, and actually in chemistry in general, of molecules which are stereochemically non-rigid. And this starts in metal carbonyl chemistry with a discussion of iron pentacarbonyl. In the 50s, it became possible to do NMR spectroscopy in a significant way, and Cotton and Waugh recorded the spectrum for neat iron pentacarbonyl. This is now the carbon-13 NMR spectrum. Rather interesting. This is done without Fourier transform techniques, with long average collections over a period of time without enrichment in carbon-13. And they see a single line. And in their manuscript on that, they say that, well, maybe we missed the other one. You'll see in a few minutes why one is not consistent with the structure. This is has a trigonal bipyramidal structure, and two lines are really expected for that NMR spectrum. Nyholm doesn't believe it. He thinks that they just have poor signal to noise, and he goes and he enriches it in carbon-13 carbon monoxide, and also records it down to -100 degrees C. And still only finds one line. And more recently, it's been done at -160 degrees C, and it's still only one line where the two were expected. Well, shortly after this result was reported, it was also known in the literature that the related molecule, phosphorus pentafluoride, also gives a single NMR signal in the fluorine-19 NMR. And this is I tried to reproduce a letter that Barry wrote to Cotton in about 1960, actually January 59. This is reproduced in an article by Cotton in the an anniversary issue of the Journal of Organometallic Chemistry for anyone who's interested in reading it. And he postulates that this trigonal bipyramidal structure perhaps is rearranging rapidly on the NMR timescale to go from one orientation to another, and at the same time exchanging axial and equatorial signals. And he suggests that the same thing happens in phosphorus pentafluoride, and that perhaps he and Cotton could write a little note to that effect. Cotton answers that this is your idea to publish it yourself, and actually Barry did in 1960 in a little JChem Phys article. He sets forward his ideas about how this should or could come about. And we now refer to it as the Barry pseudo-rotation or Barry rotation. And the fact that it's a rotation comes out in this fashion. And how it transpires is the fact that if we have a trigonal bipyramidal molecule and we look at its normal vibrational modes, some of those will take two of the equatorial ligands out and the two axial ligands in to go through a square pyramidal intermediate, and finally to a new orientation of the trigonal bipyramid, where in fact the two axial signals ligands have gone into equatorial positions. And this gives rise to the exchange, and if that's fast on the NMR timescale, it's postulated that that gives rise to the one signal. For iron pentacarbonyl in solution, that's estimated to have an activation barrier on the order of about 1 to 2 kilocalories per mole, and something that will not be frozen out in solution by NMR techniques. Now, in the early 70s, Spiess and others in Germany recorded a broad-line NMR spectrum of iron pentacarbonyl. And they go through a very complex analysis of this molecule, it turns out, and get exchange frequencies that are taking place in the solid state now for polycrystalline iron pentacarbonyl. And they argue that the Barry pseudorotation, in fact, also takes place in the solid state as well as in solution, based upon these exchange rates. Very recently, we've had a chance to look at iron pentacarbonyl in the solid state by magic angle spinning NMR techniques. And our results are shown here now for iron pentacarbonyl in the solid state, and at the similar temperature that Spiess shows by broadline NMR, we see in fact that the molecule is static in the solid state, and this Barry pseudorotation appears to be forbidden to take place in the solid state. The motions that are most likely to take place in the solid state for this molecule, back up, is not the pseudorotation, but simply the complete rotation around the threefold molecular axis of that compound in the solid state. And that most likely accounts for the line shape changes that Spiess has observed. So that's a compound that's not fluxional, it turns out, in the solid state. That also represents the first time for binary carbonyl that axial and equatorial carbonyls have been distinguished for a trigonal bipyramidal type structure. A closely related molecule to iron pentacarbonyl is the iron tetracarbonyl hydride monoanion, which the structure was reported by Bao in the 70s. This is isostructural, it turns out, with the hydrido iron cobalt tetracarbonyl compound that does the oxocatalysis. Now we have a case where by NMR we should see one type of axial ligand and 3 equatorial ligands. And in the solid state for this compound, if we look at the spectrum at minus 60 degrees C, we have the axial and equatorial signals, and these undergo the normal two-site exchange for a dynamic molecule. It's fluxional now in the solid state, giving rise to axial and equatorial exchange for these compounds, even in the solid state. And we postulate that not only can we get this threefold rotation about the principal axis, but the hydride perhaps can jump to a second phase. Rotation about that threefold axis would lead to axial equatorial exchange. We don't feel that the Berry rotation will take place in the solid state for those compounds. Now, following up on the theme of this stereochemical non-rigidity, going now to another compound. This is tetracobalt dodecacarbonyl, which is now known to have the structure B on the upper right-hand corner. And two structures in the mid-60s were gaining favor in the literature, one with C3b symmetry and one with D2d symmetry. And Cotton postulated that, in fact, you could interchange the two if you allow these bridging carbonyls to go to terminal positions to a new structure and then reclose along new edges to give this structure of the D2d symmetry. And he also argued that should this happen rapidly, that all 12 carbonyls will become equivalent on the NMR timescale. This is the first time that that it was postulated that a bridging carbonyl could go into a terminal site and vice versa. It was first shown, in fact, that does take place in this molecule, cyclopentadienyl iron dicarbonyl dimer, in about 1968 by Cotton's group at MIT, when he was at MIT. Now, coming back to Fe3CO12, if you argue that this cobalt tetramer could undergo bridge terminal exchange, and we think back to the structure of Fe3CO12 with its bridging ligands, we could argue that it opens up to an all-terminal structure and recloses to bridging positions as well. And it appears that something along these lines certainly does take place in Fe3CO12. Now, I just want to show that quickly to point out the fact that of these 12 ligands that are around Fe3CO12, they fall into the general positions of an icosahedron. And this was pointed out by Johnson. Actually, it was originally pointed out by Dahl in his original crystallographic paper, but Johnson seized on that fact to show that you could do something rather unique with Fe3CO12 in terms of its ligand exchange chemistry. If you keep the icosahedron complete and just change the orientation of that iron triangle within this icosahedral arrangement of carbonyl ligands, you go to a new structure of D3 symmetry. And Johnson argued that once you do that, you make all 12 vertices equivalent. And that could explain the exchange of carbonyl ligands in this compound. Lauer has perhaps put this on firmer theoretical footing by doing some calculations and showing, in fact, that the D3 isomer lies at a local minimum, at least by some simple calculations. If you look then to this bridge opening, here's the original structure now of the iron triangle in an icosahedron. Gives us a C2V symmetry. It could open up to this D3H isomer, which would be the bridge open isomer, or it could go to this D3 isomer. Either mechanism, though, would give the same result. That is, all 12 vertices of the icosahedron would become equivalent on the NMR timescale. Now, the NMR spectrum in solution was reported by Cotton in the 70s down to minus 160 degrees, and it's only a single line equivalent with the rapid exchange of all of these. When we looked at it originally in the solid state about 10 years ago, we found just 6 resonances now in the solid state, so some of that degeneracy has been lifted. And we also argued, based on the symmetry of that spectrum, that a certain amount of motion was taking place in the solid state. Let's jump ahead one slide. This shows our efforts at a variable temperature solid state NMR spectrum of Fe3CO12. that we did about just 3 years ago at room temperature. Now this is at a different field and a slightly different temperature, but this represents those 6 lines in ratios of 1 to 1 to 1 to 1 to 1 to 1, it turns out. And at low temperature, we can see now a bridging carbonyl that we anticipate known from the structure. And at room temperature, we see no bridging carbonyls present. Furthermore, we can correlate these signals from low temperature to the high temperature spectrum and calculate the predicted signals in the room temperature spectrum, and things work out pretty nicely. We argued then, following up on Johnson's idea that this iron triangle could move within a polyhedron of carbonyl ligands, we argued, though, that instead of going to the D3 structure in the solid state, we get a jump of one orientation of the iron triangle to a second orientation. And if, in fact, you look at the disordered structure that's observed crystallographically, our argument is that a jump from, say, the red orientation to the yellow orientation, in fact, exchanges, and while all the carbonyl ligands remain fixed in space, that gives you an exchange of carbonyl ligands in the solid state. Johnson, though, still argues that the D3 isomer can be achieved in the solid state. I would argue that that's true, but the D3 isomer in the solid state actually doesn't have true D3 symmetry and does not, in fact, lead to exchange of carbonyl ligands. Now, another compound of interest is dicobalt octocarbonyl. This is this compound with the structure shown in the top left-hand corner. These are structures generated by Lauer by molecular mechanics means, and the structures A, B, and C have all been postulated for this compound in solution. The bridge structure is what's observed in the solid state, and two terminal structures, all terminal structures have been postulated in solution, and in solution all three of those structures rapidly interconvert. Looking again now at the solid state structure, the two bridging carbonyls and this sort of eclipsed structure, at least in terms of the arrangement of the carbonyl ligands on the two cobalt atoms. Now we thought that in the solid state for this compound we should see two distinct bridging carbonyls and 6 distinct terminal carbonyls, but in fact in the solid state this compound shows just a single resonance consistent with all 8 of those carbonyl ligands being equivalent on the NMR timescale in the solid state. That's identical to the solution result, and only at minus 40 degrees do we see a bridging carbonyl and the terminal carbonyls. So these compounds can undergo, even in the solid state, can undergo a lot of rearrangement that was unprecedented before we had a chance to look at these by solid state NMR techniques. Now, that brings up to through my contributions, I think, to the metal carbonyl chemistry. I do want to illustrate to you, though, some other aspects of the chemistry of metal carbonyls. Certainly not all of the aspects of it, but there were some important developments in the synthesis of metal carbonyl clusters, and some of these are getting remarkably large, and I wanted to share some of that with you as well. We go back to some work by Heber. He developed this reductive carbonylation technique at very high pressures from the metal halides, and generated two compounds of rhodium in this particular case. One that's red. This turns out to be isostructural with a cobalt-4 compound that we've already talked about. And he argued for rhodium-4CO11 in a black structure, which Dahl subsequently showed to be the rhodium-6 cluster. Compounds now are starting to get significantly bigger. than the 3 and 4 metal atoms that we had originally that I've showed you. Dicobalt octocarbonyl, there's a typo here. That's dicobalt with 8 carbonyl ligands. Dimerizes to go to a tetracobalt cluster. That turns out to be an endothermic process that's entropically driven with the release of carbon monoxide. This cobalt-4 cluster, which we've seen, it turns out can be reduced to a cobalt-6 cluster and oxidized to this neutral cobalt-6 cluster, which is isoelectronic with the corresponding rhodium compound that I just showed you. Now, when you look closely at these clusters of 6 and more metal atoms, the numbers of electrons don't seem to add up, and they fail to follow the electron counting schemes originally proposed by Sidgwick. And the way that these are usually addressed in the literature or understood follows from a set of rules that was developed by Wade. I forgot to put his name up here, but these are referred to as Wade's rules for metal carbonyl clusters, and they follow directly from the electron counting schemes for the borohydrides and the clusters there. And if we follow through for a ruthenium-6 cluster, we take out electrons from the possibility of metal-metal bonding to accommodate all the metal to ligand bonding. And metal to ligand bonding requires 12 electrons. The total of 9 valence orbitals is the basis for the 18 electron rule. We take away those 12 electrons, it's the remaining electrons on a per metal basis that leads to the metal-metal bonding. So for this ruthenium-6 cluster, it has 86 electrons. We take away the metal to ligand bonding, and we're left with 7 electron pairs. 7 electron pairs follows the skeletal electron pair theory for borohydrides. It's giving us n+1 pairs for n vertices and predicts a closo structure. And this ruthenium-6 cluster and the rhodium clusters that I've showed you, in fact, have closo type structures and are regular octahedra. And perhaps the most recent players in the development of large cluster chemistry are Longoni and Keeney. Keeney's passed away a few years ago, and Longoni is a student of his that's continuing in the area. They show that the reductive carbonylation, this is very similar now to Heber's original reactions with base, now requires a stronger base to reduce the nickel. It forms these large nickel-5 and nickel-6 clusters, which are trigonal bipyramidal and octahedral. And then he gets these nickel-12 clusters as well as nickel-9 clusters. And we'll see some of these structures in just a minute. Let's see, I think I have one on this slide. This is a nickel-6 cluster with an octahedral arrangement of nickel atoms. Actually, an elongated octahedron so that we have 2 triangular arrangements stacked on top of one another. Longoni and Keeney also did made some similar compounds with platinum. The reductive carbonylation and the presence of base leads to this platinum-18 cluster, which fragments further under CO and base to a 15, 12, 9, and a 6 cluster. These stack in an interesting way. First, sort of an offset, eclipsed type fashion for 2 of these platinum triangles. It starts to generate a helical type structure with 3, and that becomes apparent with this platinum 15 cluster on the right. Sort of a fantastic type molecule that's growing in 2 dimensions. And I want to close, at least in terms of clusters, with a more recent work reported in '85 by Longoni's group, where he makes this nickel-38 platinum-6 cluster with a combination of a nickel-6 cluster with platinum chloride, and that platinum, shown in red here, forms an octahedral shape inside of an envelope of nickel metals, looking now like a soluble part of a metal particle. The metals now are closest packed in arrangement. with only carbon monoxide and hydrogen as ligands. Those are added on here. It doesn't take very much to take these compounds and dissolve them in solution. These look like small metal crystallites and perhaps have some application in terms of models for supported metal crystallites in catalytic applications. Now I want to finish, this is my last slide this evening with these large metal clusters. I think that's an exciting development, and a lot of chemistry is going to come out of these, I'm sure. I hope I haven't put you off too much to metal carbonyl chemistry, but given you some flavor of the types of structural chemistry that has been seen in these compounds. Our own chemistry has to do with looking at the dynamics of these compounds in the solid state. Finally, I'd like to acknowledge a few people out of my own research group who did the NMR spectroscopy. Initially, I collaborated with Professor Ed Motel from San Francisco State University with our initial work on Fe3CO12. The variable temperature work was done by a graduate student, Ed Lissick, who's now on the faculty at Tennessee Tech. The variable temperature cobalt carbonyl NMR spectroscopy was done in collaboration with Mark Sullivan, who was then at JEOL, and an undergraduate in my lab, Bob Davis. Finally, I'd like to thank you this evening. I hope I didn't show too many slides. I wanted to dedicate the talk to Larry Dahl, since I had almost a full carousel of slides. So the talk was a one Dahl talk. Thank you.
I'm sure Brian has a bit more energy left in him. And I suspect, I'm no inorganic chemist, but this sounds like good material for a Q. Those of you might have some questions for our speaker.
Yeah. I have a couple. Those fantastic structures that I guess Cotton and Wilkinson had for the
manganese.
If you stick squarate in with some iron and carbonyls, do you get anything like that? You know those ions do exist.
Yeah, no, they don't. You don't get them.
Has anyone ever tried that?
You can get compounds that have the same composition as that with squarate.
Is that right?
That's correct.
And I can't remember what the 6 one is. The 5 and the 6 CO ions are also known. I've forgotten the names of them.
You would call those something the oxocarbons.
Yeah.
No, I don't think that these types of structures have been seen from any synthetic procedure.
That more serious.
Well,
More serious question. In the iron pentacarbonyl, where you have it mined rotating in the solid state around the threefold axis.
No, I don't. Oh, yes, right.
You know, most of us who think about the solid state think of
Things as being rigid.
well, not rigid, but perhaps it could happen if it was correlated over large numbers of unit cells. Is there any evidence for that, or are there frequencies for these things, or is there?
They're activate. Okay, for that particular one, yes, there are frequencies, and they're in the range of 10 to the third jumps per second.
I only think in reciprocal sum.
Okay. Sorry, that's a simple frequency. We'd have to sit down and calculate that. I don't have an activation barrier for the threefold jump in iron pentacarbonyl, but in some of the others, for dicobalt octacarbonyl, for example, the activation barrier there in the solid state for the bridge terminal exchange is about 12 to 13 kilocalories per mole.
But particularly in the iron pentacarbonyl, where you have a 120-degree angle between them and they're sticking out quite a ways, you expect something else to be coming in there between them. There's not empty space between those carbonyls.
Yeah.
So maybe it could happen if it were
hexamethyl benzene, which also has now 6 spokes, but it doesn't have as big a jump to
Yeah,
do.
they're not nearly as out as far.
That's right, that's right. But it also jumps, and I'm not sure what the
There's
hexaethyl.
dynamics on that.
Yeah, yeah. I would imagine it's correlated, certainly. But no one has looked at and has generated any numbers on that. But this is looking at Fe3CO12. I mean, similar arguments are made as well, and that is, and I forgot to mention it after having pointed out these thermal ellipsoids. The thermal ellipsoids are rotating out of the plane, like so, and the frequencies on that are very fast. I mean, that librational motion, if you will, is a very low energy process, and that is argued by Johnson that's the only motion that's allowed in the solid state.
Intramolecular.
Intramolecular. Yeah.
It's an internal mode, not a librational.
I'm sorry. Yes. I mean, it's an internal mode. If we back up someplace, well, never mind. It's an internal mode of the molecule, and it's an out of play motion or vibration of the iron triangle, or of the iron triangle part of the molecule. And Johnson argues that that's the only allowed motion in the crystal. And I argue that that's certainly an allowed motion, but doesn't explain it cannot explain the result of the NMR spectroscopy, which is that a bridging carbonyl exchanges its chemical or magnetic environment with the terminal carbonyl. And then I argue for the threefold type jump, which is a pretty big jump for an iron atom, and activated to the tune of about 9 or 10 kilocalories per mole. So the frequencies on that jump would be.
Cobalt 2 meters before that.
I just asked. Oh no, the original crystal structure is back here. Those irons, these irons are moving in and out of the plane.
That wasn't the twin state structure that weighs solid.
This is Cotton's determination.